So hi everybody. So I'm going to present here the results of the pacemaker related experiments that we did at GFDL. So when we restored the North Atlantic. So I borrowed this slide to Kokan that presented yesterday what we did in common between NCAR and GFDL. So the primary goal of this experiment is to estimate the influence of the IMV on the climate system. And we try to understand what are the physical mechanisms that explain this different influence that we can find. And so, as Yohan said yesterday, we share a common protocol between NCAR and GFDL. So what we did is we restored the observed IMV in the CM2.1 model in GFDL. So we've got different questions. So as well. So yeah, sorry. So we try to doing the same protocol at NCAR and GFDL. We can estimate if the results are robust between models. And another question we assess is, does the climate impact of the IMV is coming from this tropical part or the subpolar part? Okay. So how do we explore the IMV path? So we restore the SST over the North Atlantic of the CM2.1 model. So CM2.1, it's 1 degree oceanic resolution on 200 kilometer atmospheric resolution. And so we restored the SST over the North Atlantic to the fixed IMV pattern as defined by Decadal 2009. And we did a 10-year-long ensemble experiment on 100 members. So in order to estimate the signal to noise of this influence. So there is basically 3 main simulations. The first one is I call the IMV+. So we restore the North Atlantic SST to its climatology, to its daily climatology, and we add on top of that fixed positive SST anomaly that is the IMV anomaly. So we've got the IMV- experiment that is the same as the IMV+ experiment, but with a shift of the sign of the IMV. And because this protocol, we expect that this protocol, restoring the model to its climatology, is going to change a bit the mean state. We did a control simulation where we just restore the model to its climatology. So the restoring is done by 8 fluxes. So the restoring is done with a 5-day time scale with a mixed layer depth of 10 meters. So that is equivalent to the third case that Christophe showed yesterday with a restoring of 120 watts per meter square per second. So it's quite soft. It's not so strong for. We are still respecting the coupling, etc. So about the IMV definition, what it choose. So here is a different definition of the IMV. So what I call the classic IMV, the trend-burst IMV, and the Ting IMV pattern. So the difference in this IMV pattern is only due to the way you remove the trend, the external forcing. So in the classic case, you just remove a linear trend. In the trend-burst case, you remove to the North Atlantic SST the spatially average SST of the globe. And in the Ting IMV, as Ting presented 2 days ago, I guess, you remove the external forcing based on your estimation from the semi-5 models. So we choose this IMV pattern because we think that it's the best estimator of the internal variability so far. But we have to keep in mind that there is discrepancy between the IMV pattern, the IMV definition, and especially in the tropics between trend-burst and Ting IMV. And I will show that it can lead to different IMV impact. Yeah. So some results quickly. So this is the 10-year ensemble mean difference between the IMV+ experiment and the control experiment in terms of surface temperature. So here the top is for the season DGFM and bottom for GGS. And here I recall the Ting HMV pattern to which we try to restore our model. So in GGS, we can see that our simulation do kind of a good job. It's a bit weaker, but the pattern is there and the structure is there. Whereas in DGFM, it's much more noisy. And we can see that in the Labrador Sea and Labrador on the super-large area region, we can't see warming. And this due to two reasons. First, in winter, you increase your mixed layer depth, so it's more noisy. And the second reason is there is a drift in the simulation, and Rim is going to talk about that later. So if you look out of the Atlantic, we can see that over land in GGS, there is a warming over extratropical latitude over land, so over the US there, over all the Mediterranean basin, and over Asia. In winter, there is no warming there, nothing significant, but there is still warming over Asia there. And we can see a strong PDO response over Pacific here. In terms of precipitation, so blue means increase of precipitation, and red and brown decrease of precipitation. So we can see in GGS an increase of the northward part of the ITZ over Atlantic, and as well over the eastern part of the Pacific. And over the western Pacific, we can see a tilt of the ISPCZ to the west, like that. And this is, we can see that as well in DGFM. In terms of sea level pressure, in GGS, we can see a low pressure anomaly over the entire North Atlantic that is mass compensated by a high pressure over the Pacific. So this is for GGS. And you can see similar things for GGFM, even if the low pressure is weaker over North Atlantic. And we can see a strong response over the Aleutian low here. So today, I would like to mainly focus over the Pacific part of the response. And I'm going to explain how this response happened. So to explain how it's happened, I just focus for the moment on the first 2 years of the simulation. So this plot represents the SST difference between the MV plus and the control simulation, so in color. And the arrow represents the wind at 850 hectopascal. So these different maps are for different seasons, AMG, GAS, OND, and GFM, so basically the time is going like that. So we can see that in AMG, we can just see a little warming of over the eastern Pacific there. And with time, we can see the emergence of cooling over the cold tongue there that is propagating westward to the central or western Pacific with time through a complete linear type signal in GFM. So to understand how this, linked to this coding, there is a wind anomaly. So I guess you can't really see the arrows there, but so there is an increase of the trade there that starts in GS and that's strengthened in October, November, December, and then strong increase of the trend in GFM. So to understand how this happened, I need this map that are basically the same as this one, but for precipitation in color, and the contour represents the velocity potential at 250 hectopascal. So we can see that in GS, we've got a subsidence anomaly over the Pacific here that indeed is caused by an increase of the convection over the tropical Pacific, over the Atlantic here, that subside here. And this is going to increase the trade over the central and the western Pacific, and finally is going to create this linear type response that we can see both in SST and precipitation there. Okay. So, as I said, we try to understand that this influence is due to the extratropical part or the tropical part of the MV. So we did 2 extra experiments. One where we restore only the MV SST over the tropical part, and another where we only restore over the extratropical part. So here is the map for is SST different in DGFM between the MV plus experiment, the control simulation still, and it's the same for these two different maps, but well. And I focus only over the year 2, 3 here. So basically what you can see is that the signal here is mainly explained by the tropical part of the MV. Yeah. If we look at this, the atmospheric circulation, with in color the zero potential at 500 hectopascal, and in contour the stream function at 250 hectopascal. So we can see that there is a reduction of the ocean low over the Pacific there, and it seems to be coherent with tropical extratropical Rossby wave anomaly. As we can see, we can follow kind of a wave train between tropics and extratropics there. And we can see that this anomaly is present as well in the tropical AMV experiment, but not in the extratropical AMV. So yeah, the amplitude is a bit lower in the tropical AMV comparing to the full AMV experiment. This suggests that this mechanism is led by the tropical AMV, but we need all the North Atlantic warming to get this strong response there. So, okay, so now I show how this anomaly happens there, but I'm going to show you that this tropical response is not stationary. So to show that, what I'm going to focus on the density of probability of the ENSO in the experiment. So this is represented by this graphic here. So the black line here represents the cumulative PDF of the control simulation. So going to 0% to 100%, and we are going here from La Nina event to El Nino event there. And the red line represents the cumulative PDF, but for the AMV plus experiment. So we can see that there is more Nina event in the AMV plus experiment comparing to the control simulation. And the blue line represents the same thing, but for the AMV minus experiment. So basically it's the opposite. We've got more Nino events in the AMV minus experiment. I forgot to tell you that this gray shading here represents the confidence interval over this cumulative PDF. And the histogram here represents the difference bin by bin between the AMV plus experiment and the AMV minus experiment. Okay, so I'm going to use this graph in the next slide to compare different periods of my simulation. So here for year 2 to 4, here for year 5 to 7, and here for year 8 to 10. So you can see that there is a cooling during these years, but then it's followed by slightly warming of the tropical part, the Pacific, and then we are going back to Nina condition. And indeed, if we look at this PDF graphic, we can see that the red line and the blue line switched, and they are just the opposite of what was during these years, during the years 5 to 7. So that suggests that during this year, there is finally more Nino events than Nina events in the AMV plus experiment comparing to the control simulation. And finally, we are going back to the same thing at year 8 to 10. So I try to understand why this happened. Is there also predictability and ENSO? But so to understand why this happened, I have to say some word of ENSO in this model and of ENSO in general. So what I did here is I compute a composite of the Nino-free SST index in my control simulation. So I select the Nino and Nina events based on a threshold of plus or minus 1 standard deviation of the Nino-free SST index. So here the dashed line represents the maximum of the Nino events that I choose for in January. So just yeah, okay. And every line represents all the different events that I obtain. So we can see that some event peaks before January, some peaks twice in January and then the next year, etc. So there is a lot of different behavior in all these events. So, but here I just want to focus on the canonical ENSO behavior. So I did that by computing the ensemble, the mean of this composite that is shown in bold lines there. So if I only keep that, so I got this line. So we can see that after a Nino event, we then got a cooling that seems to stay for at least 2 years there. Yeah, here's the time in months. Right, and for Nina composite, we can see that after Nina composite, there is finally a warming, a slight warming, but still a warming of the tropical, of the Nino-free index, Nino-free zone, here during 2 or 3 years. So how this can be related to my experiment? So now this represents the Nino-free index, and here the dashed line now represents the starting date of my simulation. So as we saw that there is more Nino events in my MV- experiment during the first 3 years. But what does it mean concretely? So here I represent one member that got the same behavior than this canonical ENSO here. So it just I just represent the same thing here, but just zoom in. So you can see that if one member shows a Nino event, it's not going to be warm for 3 years. What's happened is going to cool down after the first years, and then it's going to show cooling. So if there is warming during the first 3 years of the experiment, it's not because only of one of all members that show warm condition during the 3 years. It's because there is warming for one member over the first years, and then another member is going to show a Nino event the second years, and etc. During the third year, another member is going to show that. So when I average over the 3 years, and I average over all the members, I obtain this kind of residual. And we can see that there is a warming here during the first 3 years of the simulation, and then is followed by cooling. And for the NIA composite, so that means the MV plus experiment, it's similar. There is a cooling over the first 3 years, and then it's followed by weak warming there. So this is done by just hand. So is it really what's happened in my simulation? We have to test that. So what I represent here, it's still the SST ensemble mean difference between the MV plus and control simulation in DGFM for the year 2 to 4. So as you already seen before. Okay, on year 5 to 7, or 8 to 10. And here, it's the same thing, but for a subsampling of the ensemble members. So I choose only the NINA members. So what I call NINA members is the members that show at least one NINA event over the first 3 years of the simulation. So by construction, I've got a strong cooling over the first 3 years here. But what is interesting is to look at their evolution. So you can see that there is, after this cooling, there is finally warming. And then we are going back to NINA condition. And if I do the same with the members that doesn't show NINA events during the first 3 years, finally, we can see that there's no cooling at first. And then there is weak cooling in the years 5 to 7, and then NINA condition. So this suggests that the switch between NINA to NINO and then to NINA condition in this experiment is indeed due to the ENSO behavior. Oh, thank you. Okay. Yeah, that's it. So now I want to ask, does the North-Pacific response here is effectively due to the ENSO response? So to do so, I did an additional experiment where I restore the North-Tropical Pacific to its climatology. So I just cancel ENSO here. And what you can see is that the North-Pacific response is mainly due to the ENSO anomaly that occurs in the tropical part here. So this is true for the year 2 to 4. But if we look at longer time scale, so if I average over the 10 years of my simulation, so there is this PDO kind of like a response here. And finally, we can see that even in this experiment, we still have this PDO response. And if I look at the extratropical North Atlantic experiment as well, we can see that this PDO response at year 2 to 10 is as well present as well. So this suggests that there is another teleconnection between the Atlantic and the Pacific that is caused by the extratropical part of the thing. So yeah, so here's the conclusion of my talk. So we saw that a positive phase of the MV leads to an increased occurrence of the NIA events in the first years, and then as well to a setup of a PDO, of a negative phase of the PDO. We saw that the ENSO response is forced by a tropical part of the MV, whereas the PDO response is forced both by a extratropical Pacific teleconnection, so related to ENSO, but as well to extratropical Atlantic Pacific teleconnection. So that's it. Thank you.
Thanks. Any questions?
I think it's a very nice demonstration of how ENSO really interferes with the longer time scales. And because you are setting up this experiment as a startup experiment, then you're actually getting a mix between the ENSO tendency to have some sort of a cycle. I think it was a very nice explanation. But what I wanted to say is that Axel Timmermann has already pointed out earlier that what happens because of the AMO or AMV is that you do tend to lift, you tend to get that intensification of trades and lift the thermocline, and then tend to get the preference for La Nina conditions, and that sets up the entire thing. And the last thing I wanted to ask, so if that works like that, why don't we get predictability in the Pacific from, we do have predictability in the AMO, so why don't we get predictability in the Pacific?
One possibility is because, so this is a pattern that we impose in the simulation. So we got a strong tropical warming, and in the couple model, the MV doesn't show this strong warming here.
In the model, usually you don't get that.
Yeah, it's not so strong. So this could explain why there is not this tropical teleconnection. One reason. And so maybe we lost this predictability on North Pacific as well.
Working back, Doug.
So that's a fascinating set of results. Thank you. So I have two small questions. So one, if you get to your very first winter response in terms of sea level pressure, do you see anything in any area?
The first win.
Very first winter.
So I got, yeah, I don't have to show that today, but yeah, we can I show this plot? Yeah, cool. Okay.
So the other one was this fascinating.
But yeah, there is definitely something in the North Atlantic, but it may be highlight something else.
So have you got a mechanism for that second extratropical one?
We still didn't work so much on it, but I think Zhang and Delworth in 2007 explained this mechanism by the storm track activity that may link the extratropical part of the MV to the extratropical Pacific. Yeah.
I'd like to ask about the metrics that you use, because it might be different from other people, and it might make it hard to compare. You use DJFM in some of your figures. You use JFM in other figures. How did you decide how to define the season? And also you used Nino 3 rather than Nino 3.4, which is more conventional. How did you decide to use that to define the Nino? Because if you're comparing to other people that use different metrics, it might be confusing.
So for the season, I just show once, only 3 months. It was just for this thing here to understand.
But why didn't you use DJF, which is the traditional winter definition?
The only reason is because I just split the year in 3 months, and that was the only reason for that. For the DGFM?
Well, the traditional season definition for winter begins on December 1st, not January 1st, and so I just wondering why you...
Yeah, but here it's... Yeah.
Doesn't affect.
Yeah, anyway.
It's not sensitive to the definition.
It's not sensitive to the definition?
It was just easier for me to split in 3 months, the years. So that's the only reason I did that. But after I just showed DGFM everywhere, so and it's really similar to what I obtained in GFM here. So if you can see here, it's really similar to what I obtained here. So.
And why Nino 3 rather than Nino
Linear free is because I was just looking at the temperature anomalies. On linear free flow, I think it's a mix between temperature and wind. So I just look at linear free.
It's just it just adds another segment to linear free. It goes a bit west.
It's not shift a bit. So yeah, but the thing is here, so in this plot I chose linear free, but here it's not linear free. It's actually an EOF based on the temperature average over the first 200 meters of my tropical Pacific, and I just compute the first EOF, and then I project all my members on this EOF. So I mean, the dynamics is really ENSO dynamics, even if I choose linear free or ENSO reservoir. I think it's not sensitive to this.
Yeah, so the result is very consistent with our results Atlantic induced Pacific due to the Walker circulation. But I'm just wondering, in the Atlantic, tropical Atlantic warming is affected there. But how? I'm just wondering, is it really tropical Atlantic warming, or is there some meridional gradient in tropical Atlantic that affected? Was there? In other words, what is the rule in southern tropical Atlantic? It doesn't matter in condition, or it's still.
So
Because in this case, we can see the meridional gradient in the tropical Atlantic. So I'm just wondering if southern tropical Atlantic is much warmer or colder condition. Is there some impact to the Pacific or
check that.
what is the reason?
No.
We think no.
But
So I noticed you, in this case, you don't have very strong Atlantic response, most Atlantic response, and the negative and there also response. So I was wondering if you compare this with the actual models and in a couple of models.
yeah, I still didn't do that. But as I say to Yohan, I think the tropical signature of the model HMV is weaker. So yeah, I have to check.
But I think partially it could be because your model in this kind of setting, your tropical Pacific SST is so strong that could compensate for some of the response to the Atlantic SST.
This is what's happening here. For the winter anyways.
Oh, the okay. Sorry, I didn't catch your question.
No.
So this results, I mean, you find this on the seasonal time scale. There's quite a lot of work showing that both the equatorial Atlantic SST and the north tropical Atlantic SST tend to lead the ENSO signal for 6 months or so. So I think this is very consistent. It's very nice. It seems, if I'm not mistaken, that the response in the Pacific depends on the model having a skewness in ENSO. Right? Is that true? You have a rectification effect. Isn't that what I see just even on that figure there?
Skewness of ENSO.
So if you have a positive, if you have a negative in the Atlantic, you will tend to get the positive phase in the Pacific, right?
Yeah.
Right?
Yeah.
And the other way, I wouldn't expect such a strong response if the La Niñas are weaker, right? La Niñas are stronger than La Niñas.
Yeah.
So the figure you showed before, right? The next 2 or 3 are wrong.
So what?
Isn't it because it takes 10 years and you get one La Niña and La Niña and La Niña dominates?
Well, I mean, but La Niñas are much stronger than La Niñas.
Oh, yeah, but actually, but if you look at this, I catch your question.
But if you look at the figure, that figure there, the one before that.
So if you look at this composite here, there is a linear element there, but then there is a weak, very weak. So that could be a reason why the linear anomaly doesn't dominate the signal. But if you compare the free this map here and this map here, it's only an average over the first 3 years of simulation, so there is a really strong cooling here. But when I average over all the 10 years, the cooling is much weaker, so it can be due because I've got much more sample. But as well, because in this average, there is as well Nino events at taking into account. So I think the Nino event just reduced my signal. Okay.
Okay. Thank you very much.